Welcome back. In this class we are going to study about the layout using Nmos logic. Now first of all, just quickly recap what is meant by layout. Layout is nothing but geometrical representation of stick diagram. Now what is meant by stick diagram? Absolutely. Conveying layers information in the form of color code or in the form of monochrome encoding. Is it okay? Now for that stick diagram, if you apply geometrics, then it becomes what? Layout. Now you can observe on the screen, I have considered an example of Nmos inverter, okay, which is a 4:1 Nmos inverter. Then if you observe that the pull up ratio is 4:1, the pull down ratio is 1:1. If you consider overall from pull up to pull down, then the ratio becomes what? 4:1. Is it clear? Now you can observe this stick diagram, and since it is a depletion mode Nmos, then you may have an implant here. This is an enhancement mode Nmos, therefore you do not have any implant here. Then this is a metal, this is a metal, and it is VDD and it is VSS. All these things we had discussed in the previous classes. Now here the focus is to design the layout of an Nmos inverter or some other examples using Nmos logic. Is it okay? Now you can observe that I am considering one metal. Now you may observe I am going to design a layout and I am considering a metal. Now you can talk about this is my metal. Okay. Now in Nmos, this metal itself what? VDD. Therefore I may write this is VDD. Okay, I will write clearly. Yeah, this is VDD. Okay, now I have to consider here. You may observe that one more metal. Then I can call this metal as what? Absolutely, I can call this metal as VSS. VSS. Is it clear? VSS. Now you require a diffusion here. Therefore, since only one diffusion is going to be used in Nmos logic, what is the diffusion? Absolutely, N diffusion. Therefore, I am considering an N diffusion here. You can observe very clearly. I am considering an N diffusion. How we discussed that the representation of N here? Absolutely, in this fashion. Is it clear? Now you require two contacts. Now I require a contact. Now I have to represent a contact. Then I required a metal area. Okay, this is my metal contact area, and I required a contact cut in between. This is a contact cut, and the metal it is a combination of what? Metal and diffusion. Since diffusion is already present, I hope that are you clear. Now here also you can observe that you required a metal. That means contact area we required. I will draw some more clearly. You can observe here. Yeah, absolutely. Then you require a contact cut. Okay. Now here metal should be there and diffusion is there. Now here very important point is we have to draw a depletion mode MOSFET and enhancement mode MOSFET. Therefore I have to cross polysilicon. You may observe that. How I'm going to draw that is an important point for you. This is the way. Let us consider a different color. in this manner you have to draw. Remember that very importantly. Okay, this is what polysilicon. Okay, this is a polysilicon. Now you require an implant. You have to draw an implant in this fashion. Very carefully you can observe. It should be exactly like this. Okay, this is an implant. I hope that are you clear. Okay, and you require a buried contact here. You have to represent a buried contact. Okay, this is how you have to represent depletion mode MOSFET. Now remember, in NMOS logic, pull-up network won't be changed. Only pull-down is going to be changed. Therefore, the pull-up network is same. And you require one more transistor. What is the transistor? Enhancement mode transistor. Therefore, I have to cross this one, and I don't have sufficient space. Therefore, I am representing it as V in and it as Y. I hope that are clear. Now this is layout, and don't forget, according to definition you should provide what? Geometrics. Therefore now I am providing the geometrics. If you want to observe, what is this? Absolutely, since it is a metal, what is the minimum width of metal? 3 lambda. Since it is a poly, what is the minimum width of poly? 2 lambda. Now since it is an implant, what is the minimum size of implant? 6 lambda by 6 lambda. Next, if you observe that contact area, you are having a contact area. Okay, you can write what is this size of contact area? You can clearly write. What is its size? Absolutely 4 lambda by 4 lambda. You can talk about this one. Okay, 4 lambda. Is it understood, all of you? Or you may represent here also. This is 4 lambda. Sorry for that. This is 4 lambda. And from here to here also you may represent. This is 4 lambda. Okay, now it becomes layout. Is it understood, all of you? Okay, that's it, guys. In this manner you have to represent layout of Nmos logic. Okay, don't forget this section. Once again I'm telling that this section won't be changed. This entire section won't be changed. It is same for every logic. Just the pull down is going to be vary. Is it clear? Shall we see some other one? Yeah, absolutely. Directly I am going to draw layout. You can observe that. Okay, now if they ask us to draw the layout of 2 input NAND gate, we know that in the 2 input NAND gate Nmos is connected in series. This is similar, and it becomes A, and it becomes B, and it is output. Now I am going to talk about layout. You can observe the layout here. First, what should we have to draw? Absolutely, metal we have to draw. Don't forget, you have to complete stick diagram then you have to draw layout, but I am directly here representing the layout. You can observe here, this is my metal, sorry for that. Okay, I can understood when I am pulling this one, it is coming, right? Yeah, sorry for the delay. Okay, this is my metal here, and you can observe this is my metal here. Now it is what VDD, it is VSS. Now you know very well you have to draw a diffusion, since it is Y closely represent. Okay, then you required a contact here, therefore you should draw contact area, and you should have a metal, and here also you should draw the contact area and a contact cut. Okay, and you should have what? Metal here. Now what I said to you, the pull up won't be changed, therefore don't change the pull up. Draw as it is we have how we have seen in the previous example. And I said you to take this implant in such a fashion this is an implant, and I said you to give the burr rate contact in this fashion. I have to give the burr rate contact by reducing the thickness of the color. This is your burr rate contact. Now you can observe how many transistors are there. 2 transistors are there, therefore you have to consider 2 transistors. That means 2 polysilicons. This is A, this is B. Now you have to apply the rules. What are the rules? This is what? 3 lambda. Okay, this is what? Polysilicon. This is 2 lambda. And these also what? 2 lambda. And the minimum separation between poly to poly is also what? 2 lambda. And implant to transistor is what? 2 lambda. And implant to other transistor is also what? 2 lambda. And the contact area is what? 4 lambda. And the contact area is 4 lambda. And in this manner you have to complete what? Absolutely. What is that? Layout. Okay. If you are having similar type of figure like this, let us consider 2 input NOR gate is like this. If you are having 2 input NOR gate, then this portion, once again I am telling that it is same. Up to here it is same. After that, what should you have to do? You have to write like this. After that, you have to take Okay, then you have to consider, and you have to give a contact cut here, you have to give a contact cut here, then you have to cross your polysilicon in such a manner. I hope that are you clear. In this fashion the layout of NMOS logic is going to be implemented. If you are having any queries, please comment. Okay, have a nice day. Thank you very much for each and everyone. Have a nice day.